Ah, okay.
Good morning, good afternoon. It is a great pleasure to introduce today's ISQGD distinguished speaker, Professor Károly Simon from the Institute of Mathematics at the Budapest University of Technology and Economics. Professor Simon is a leading figure in modern fractal geometry, dynamical systems, and ergodic theory, and his work has had a profound and lasting influence on these areas. Professor Simon's research spans a wide range of topics, including iterated function systems, self-similar and self-affine sets and measures, dimension theory, random dynamical systems, and overlaps in fractal construction. He is particularly well known for his deep contributions to the dimension theory of hyperbolic iterated function systems, conditional measures, and the fine structure of invariant measures arising in dynamical systems. In today's lecture, entitled Dimension Theory of Hyperbolic Iterated Function Systems, on the line, Professor Simon will discuss fundamental ideas and recent developments concerning the dimension theory of dynamically defined fractal sets, a topic that lies at the crossroads of geometry, dynamics, and analysis and connects naturally with the core themes of ISQGD. Please join us in warmly welcoming Professor Károly Simon to the ISQGD Distinguished Lecture Series.
So, can I share?
Yes, please.
Okay. Hopefully, this is shared. Do you see it?
Yes, we can see.
Oh my God, this. So you see that my screen.
Yes.
Good. So the title. Thank you very much, Marina, for inviting me to give this lecture. And the title is Dimension Theory of Hyperbolic Iterated Function System. On the line, as Marina has already mentioned, and all new results. I will start with an introduction of classical results, but all new results are joined with Balázs Bárány from Budapest and Adam Spivak from Warsaw and Boris Solomiak from Barilan University. Okay, so what is a hyperbolic iterated function system? On the line, I just drew a picture about it. So the iterated function system is usually it is denoted with capital F. It is a finite list of self maps of a certain usually in most general setup a complete metric space, but in our case we will be on the real line. In particular, there is an interval, an open interval, which we denote by V, and a closed subinterval, which is denoted by X, as you see over here. And these mappings, F consists of M mappings like this, and we write for this alphabet the integers from 1 to M, we write capital A for it, and this capital and this interval capital X is mapped into itself by each of these mappings. In this picture, M is equal to 3, as you see. So what we assume it is that FIV, this is a bigger interval, so V is an open interval which contains this closed interval X, and FIV is subset of X, and FIRC are diffeomorphism on V, and FIX is also subset of X, and what we assume it is that the derivative is strictly separated from both 0 and 1. What is R? In general, it is enough to assume 1 plus epsilon, or even R is equal to 1. But for the simplicity in this talk, many cases we assume R is equal to 3 But in many the classical results, as far as the new results are concerned, I will require R is 3, but for the classical results, it's enough 1 plus epsilon. Okay. So what is the attractor? The attractor is what remains after infinitely many iterations. If we start, so one more time, I show the picture. So if we start from this X, which is this interval, and we iterate the system infinitely many times, and whatever remains after infinitely many steps, it is the attractor. The attractor satisfies this equation. So the attractor is the unique non-empty compact set which satisfies this equation. Now the level 1 cylinders are the sets of this form, and the level n cylinders are the sets of this form when we use this shorthand notation for the n-fold iteration of fi1 fin. Just we write f sub i1 in, and then on the previous picture, we could see that these are this X3 and X2 and X1. These are the first cylinder, and I will, in most of the situations, I considered, I assume that there is some overlap in between these cylinders, because otherwise it's the dimension theory has been understood very well for a long time. So these are the n cylinders, and it's easy to see that if you take the union of all n cylinders and you take the intersection, it gives you back the attractor. I believe that everybody who listens to this talk knows what is the definition of the Hausdorff dimension, but nevertheless, I just wrote it down here. What we will use several times, it is the so-called pressure function. The pressure function is going to be very, very important. So here in the definition of the Hausdorff dimension, we just take all possible covers, but if you focus on the cover with the level and cylinders, and the sum, which is this green sum, is going to be this green sum in that case. So what is the pressure function? We just choose a t, which is non-negative. It's a non-negative real number, this t, and then we take the cover. You see this yellow union. It shows that this union is a cover of the attractor. Now, if we do not consider all the covers, but we focus on the cover with the level and cylinders, then this green sum becomes this green sum. So this is the most natural cover. And then if we consider the exponential growth rate, this is the exponential growth rate of the green sum, then we get the so-called pressure function. It will be very important, and then it's easy to see that this equality holds here. This means that the diameter, so here we take the diameter, these two vertical lines means the diameter, or in this case the length, because this is simply an interval, a closed interval, and its length is this, and we raise the length to the power t, and then we take the exponential growth rate, and this exponential growth rate is the pressure function. You can see that if the pressure function is positive, so the exponential growth rate is positive, then this green sum is exponentially large in n. If the exponential growth rate is negative, then this is exponentially small in n. So it is a good guess that the root of this pressure function could be a good candidate for the Hausdorff dimension. And oh my God, this is something strange happened. I pressed something I shouldn't have pressed. I'm sorry. So I'm sorry. Okay. Okay, I can go further. So I have this kind of habit that whenever I write these two boxes, then what you see in the gray box, it is what we have already mentioned and we have already gone through. This is just to recall the already mentioned facts which are relevant to understand what is in the green box. The green is the new and the gray is the old always. So this is what we have already mentioned. And then here is the definition of the pressure function. And then it's easy to see that the pressure function is continuous and strictly decreasing, and at zero it's strictly positive, and infinity it is negative infinite. So it has a unique zero. And we will use this several times, this unique zero. I mentioned you earlier that the zero of this pressure function is the most natural candidate for the Hausdorff dimension. We may call it conformal similarity dimension. So this SF, this is the unique zero of the pressure function. And from this argument that I gave earlier, it is clear that the Hausdorff dimension of the attractor is more than equal to this similarity dimension. Actually, in many cases, we would like to prove that they are equal to. So this SF, the root of the pressure function, is the most natural candidate. And we would like to prove that in some sense, typically, this is going to be actually the Hausdorff dimension. Now, we need to consider the symbolic space. And the symbolic space is just, I recall that A was this alphabet 1 to M, because we have M functions. I make it a little smaller and write a little bit. So A was this set from 1 to M, and the set of all infinite sequences from A is the so-called symbolic space, A to the power N, and we can consider this distance we are going to. So this is a metric space with this distance. This is probably the most natural distance we consider it. And another important thing is the N cylinders. So if you pick an element which is an infinite sequence I, which is just I1, I2, In, so you consider such a sequence, and then when you want to restrict it to the first coordinate, then we denote it by I restricted to the first N coordinate, and then it determines a cylinder set in the symbolic space, which is the collection of all infinite symbolic sequence which are the same in their first N digit. They agree with I in their first N digit. So this is the cylinder set in the symbolic space, and the natural coding appears here. What we call it sometimes natural projection. Okay, so we write E sigma for the collection of ergodic invariant measures on the symbolic space, and for a measure which is an element of this E sigma, we can define the entropy, and we will define the Lyapunov exponent. The entropy is given by this. So this is the exponential growth rate of the measure of this cylinder. We just consider the one more time what was this cylinder. This IN cylinder was the collection of all infinite sequences such that JK was equal to IK for every K smaller than or equal to N. So these were the N cylinders, and if you take a typical element of a mu-typical element of sigma, and then you can consider the measure of the N cylinders, and this is an exponentially decreasing sequence, and the speed of exponential decrease is the entropy, basically. So it is written like here that the measure of the n cylinder is approximately e to the power negative n times h mu. So this h mu, which gives the speed of the decrease of the measure of a typical n cylinder, it is the entropy, and the Lyapunov exponent is somehow similar. So if you take a typical the diameter or the length of a typical n cylinder, this is an exponentially small number, and then the speed of this exponential decrease is the Lyapunov exponent. And then we can define this ratio, which is the similarity dimension of the measure. This is entropy divided by Lyapunov exponent. And I would like to recall, I believe most of the colleagues in the audience know what is the Hausdorff dimension of the measure. This is actually the upper Hausdorff dimension, but I just wrote Hausdorff dimension. It is the infimum of Hausdorff dimension of full measure sets. And what is the lower Hausdorff dimension? It is the infimum of Hausdorff dimensions of sets of positive measure. In many cases, what I will do it is that mu we refer to a measure, an ergodic sigma left shift invariant measure on the symbolic space. It is going to be mu, and this push forward measure with the natural coding, this pi was the natural coding, so that with the natural coding, this push forward measure is going to be nu. So mu is in the symbolic space, and nu is a measure on the attractor. Okay, so it was proved by Feng and Hu in 2009 that the Hausdorff dimension of the attractor is actually the supremum of the Hausdorff dimension of the push forwards of the ergodic invariant measures. Now it is well known that the Hausdorff dimension is smaller than equal to the minimum of 1, and this SF mu, which was defined as entropy divided by Lyapunov exponent. Now, if the open set condition holds, which means this, what is written here in red, I believe everybody knows that. So if the open set condition holds, then the Hausdorff dimension is indeed equal to this conformal dimension. Sorry, this conformal dimension, or by some people conformal similarity dimension, whatever, this SF, which was the root of the pressure. And if the open set condition holds, and nu is push forward of this ergodic measure mu, so one more time, mu is an ergodic measure on the symbolic space, and nu is its push forward to the attractor. So this is nu. Then the Hausdorff dimension of nu is equal to the similarity dimension, which is entropy divided by Lyapunov exponent for this measure mu. This has been known for a very long time. These are very, very classical results. I don't even know who proved them for the first. So if the open set condition holds, which means that the cylinders are somehow well separated, there are some overlaps, but the overlaps are not important. And what we would like to do during this talk, one of the two most important aim is to prove somehow that typically similar sentence holds, assertions holds, even if we do not assume the open set condition. Now we will need something from dynamical system. This is a result from Bauern's book. If you have a Hölder continuous function, phi is a Hölder continuous function we call it further continuous potential. So this is a function on the symbolic space, and it takes values in real line. So this is further continuous. Then there exists a Border probability measure, and we may assume that it is sigma invariant and ergodic, which is called mu, and mu is supported on sigma, and the constant such that for every finite word, so the star means finite word, such that every finite word, this mu I divided by the exponent of whatever you can see here, this is the topological pressure of phi. I would not define it here. We just use it a little later. So such an identity hold. This is a very, very important measure, which is called Gibbs measure for the potential phi. We consider iterated function systems. This theta gamma 1, gamma 2 means that all the derivatives, so this theta m gamma 1, gamma 2, this is the collection of those kind of iterated function systems f I when I goes from 1 to m, where we have that the derivative, so this is the derivative in absolute value is bigger than gamma 1 and smaller than gamma 2. So the derivative is uniformly separated from 0 and 1, and we always assume that this gamma 1, gamma 2 is strictly in between 0 and 1. So we consider this kind of iterated function systems, and we define this potential, which is simply the logarithm of the derivative of fi1 evaluated at this point. We assume that it's sufficiently smooth, and we can consider the Gibbs measure not for this potential, but this potential phi, what we get in a way that we multiply this previously mentioned red potential with SF. So if we take this product, this is the number which is the root of the pressure function, and we multiply it with this potential, then this yellow potential is called the geometric potential. We call it geometric potential, and this pressure for this geometric potential, just because SF is the root of the pressure function, so the pressure, if this is phi, then the pressure for this geometric potential is equal to 0. So this very complicated formula, what I didn't want to detail, it will be as simple as this. So if you consider mu, which is the Gibbs measure for the geometric potential, then this complicated formula in Bowen's book, it simply says that the measure of an n cylinder in the symbolic space, the measure with this Gibbs measure for the geometric potential, is up to a constant as big as the length of the corresponding n cylinder. So this is an n cylinder in the symbolic space. You take the corresponding n cylinder on the attractor, and you take its length and you raise it to this power SF, where SF was the root of the pressure. So one more time, the pressure function, the root of the pressure, this was the definition of SF. I'm sorry. So this was the definition of SF. So this is really a very, very important measure, even if you did not, those who are not very familiar with dynamical systems, if they did not follow it very closely, this theorem, which we did not detail too much, but it says that there is a a measure which is sigma invariant and ergodic on the symbolic space, such that the measure of an n cylinder is almost, this is just up to this constant, the length of the corresponding n cylinder on the attractor raised to the power SF. So this is, you can see that this is an enormously important measure, which is the Gibbs measure for the geometric potential. So this is the most important measure for this iterated function system. And here this gray was, again, I just wrote down what we have already considered. So this is the similarity dimension for the measure, and this is the Gibbs measure for the geometric potential. Now we consider this mu and its push forward, this nu, which is the push forward of mu, and then it is well known that if the open set condition holds, then the host of dimension of nu is equal to the minimum of 1, and this entropy divided by Lyapunov exponent, and this is equal to minimum of 1 and SF, where SF was the root of the pressure, which is the host of dimension of lambda. So if the open set condition holds, then this measured nu is the one which is the push forward of the Gibbs measure for the geometric potential, and its dimension, the host of dimension of nu, is equal to the host of dimension of lambda. Now we will need another separation condition, which is not as strong as the open set condition. This is called exponential separation condition. It simply means that there exists a sequence of indices nk such that if we consider every nk level distinct cylinders, so these are cylinders which are which means that they are words above the alphabet A of length nk, such that they are distinct, then the corresponding mappings, if you consider the corresponding mappings, these are nk-fold iterates, and these are nk-fold iterates along I1 ink and J1 jnk, then if you take the supremum norm of this, the difference of the two functions, then the supremum norm is at least c to the power nk. So the exponential separation condition holds if there is such a positive constant that this difference, the supremum norm of this difference is c to the power nk for every I and j. This is the exponential separation condition. In this case, yet again, I just repeated many definitions like the exponential separation condition, the similarity dimension of the measure, and also the definition of the pressure function and SF, which was the root of the pressure function. So here is a very, very new theorem of Rappaport, which says, it is really a great theorem, that which says that if X is a compact interval on the line and we have this iterated function system F, which consists of M mappings above X, and we assume that these mappings are real analytic, and this system is not a degenerated system, so there is no common fixed point, and we assume that this exponential separation condition holds, which was mentioned previously, then if we take any probability vector and we consider, let mu be the corresponding product measure on sigma on the symbolic space, and we consider the push forward of this infinite product measure, then the host of dimension of nu is going to be the minimum of 1, and this similarity dimension of the measure, which is entropy divided by Lyapunov exponent. And for me, even more interestingly, the Hausdorff dimension of the attractor in this case, so the real assumption is that the exponential condition, the exponential separation condition holds. So under this assumption, the dimension of the attractor is really the minimum and the root of the pressure. Previously mentioned that if the open set condition holds, then this formula holds, but this exponential separation condition is a much more mild condition than the open set condition, and this is a great achievement indeed. But I like to mention that this assumption is very important, that these functions over here are real analytic functions. Okay. So this was Rappaport's theorem. Now, but if you do not consider functions which are real analytic, then we do not have such a nice result. And the only thing what we can do at the moment is that we consider not one particular iterated function system, but a family of iterated function systems. And we would like to find out what happens about the dimension, for example, for a typical element of this family. So from now on, we are going to consider families instead of individual iterated function systems. So these kind of things like f lambda, this is a family. So there, if this is a family, then there are some parameters. So in our case, the parameter domain, which is U, it is contained in RD, and U is the closure of its. So U is an open set, and this is the parameter, which is the closure of its interior. So it's a kind of regular domain in RD. So this is the parameter domain. And for each lambda from this parameter, we are given an iterated function system, which is such a hyperbolic iterated function system on the line, what we considered. And we say that this together, this blue, is a continuous family of smooth hyperbolic iterated function system on the compact interval X if some condition holds. The first condition is that the derivative with respect to X is uniformly separated for the entire family. So for all I, so for all J, and for all lambda, for all parameter, they are uniformly, the derivative uniformly separated from both 0 and 1. And then we started with this interval V and X at the beginning. They are uniform for all members of this family. And one more assumption, which is a very strong technical assumption, just because I don't want to detail in every theorem later what are the exact assumptions. Therefore, I assume something strong, namely that if you consider this mapping, this yellow mapping, in this yellow mapping, you see in the left-hand side, there are d+1 variables, because lambda is an element of U, and U is subset of RD. So this means already d variables, and X is from the line. So this is d+1 variables, and we consider this mapping. And this mapping, so all the third partial derivative with respect to these d+1 variables, all the third partial derivatives exist and continuous. Usually we don't need to require that much, but if I require that, then all the theorems holds, and it's easier to do so. So if all of these things happen, then we say that this blue family is a continuous family of smooth hyperbolic iterated function systems on the compact interval X, if all of this happens. And from now on, I will always assume this. So one more time, all the derivatives are uniformly separated from 0 and 1, uniformly both in the parameter and which map all the iterated function system consists of the same number of mappings, and they are defined on the same interval. And here we need to say that there is a real smooth dependence on the parameter, which means that this mapping is all the third partial derivatives are continuous. So this is the continuous family of smooth hyperbolic IFS, and whatever I say, it always relates to this. So it's such an example, which will be our very important example of family of vertical translates of small iterated function system. So consider such an iterated function system, hyperbolic iterated function system on the line. All the mappings are C3, and that's all. So we start with this, but we also assume that the derivatives are smaller than 1/2. That's why I say that small iterated function system, because all the derivatives are supposed to be strictly smaller than 1/2. Now you choose some positive epsilon, and you can consider, because there are m function, you can consider this cube in the m-dimensional space, this red cube, and then a translation of this original iterated function system with f lambda. So we define f1 lambda and fm lambda, when f1 lambda is just this vertical translate of the original function f1, and fm lambda is the vertical translate, just the vertically translated with lambda m. So in this case, the parameter domain is this set U, and we call this f lambda a vertical translate of f, and this is going to be a smooth. So this will satisfy, the assumptions what we posed previously. So this is a continuous family of smooth hyperbolic iterated function system on the and whenever I say such a continuous family, you can think of this particular family, because this is one. Okay. So we will need about the family another condition, which we call transversality condition, but this is a higher dimensional transversality condition. And any of these three, here are actually three equivalent conditions. One of them is called T-like transversality, T2 and T3. So there are altogether three conditions. I would just stick to the second one because it's easiest. It means that there exists a number theta, which is a positive number, such that for every parameter and for every infinite sequences from every code from sigma, if the first digits of the codes are different, and if pi lambda I is equal to pi lambda j, then the gradient, because this funny thing is the gradient of this different is the length of this vector is at least theta. So there is such a theta that if for any, this is a strong assumption, because it says that there is one theta such that for any parameters and any codes with different third digits, if these codes I and j, they code the same element of the attractor, then the difference, so if this difference is zero, because they are equal to each other, it means that the difference is zero. So if the difference is zero, then the gradient is big. So this is one version of transversality, but I wrote two more versions. This is in higher dimension because U is supposed to be subset of RD. I would now, just because I do not have too much time, I would focus on this. So if U is one-dimensional, then you can imagine that this is the parameter domain, but I show you here. And you fix an I, you fix this I, and then for different lambdas, pi lambda I is such a beautiful curve. And if you fix a j, then for different lambdas, pi lambda j is this blue curve. And the transversality condition says that maybe this blue curve and red curve, maybe they do not intersect each other. But if they intersect each other, then the intersection is transversal, so the angle in between the tangent line at the intersection point is uniformly bounded from 0 from all for all I and j. This is the transversality condition on the line and in higher dimensions. So you see that if pi lambda j and pi lambda I are the same, then the derivatives are different. And you see that here what I said, that if pi lambda I and pi lambda j are the same, then the gradient of the difference is uniformly separated from 0. So this is very similar in higher dimension, but it can be drawn in dimension 1 better. Okay, so we had a theorem very long time ago with Boris, actually 2 theorems, but I just mentioned one of the 2 with Boris Solomiak and Mariusz Urbanski, that we considered such a continuous family which satisfies the transversality condition. Then we proved that for Lebesgue almost all parameter, Lebesgue almost all parameter, the host of dimension is what of the attractor is what it needs to be, so it is the minimum of 1 and the root of the pressure formula. Or if this S f lambda, which is the symmetry dimension, is bigger than 1, then the attractor has positive measure. We also proved a variant of this theorem for measures. But I don't want to write it now. So from now on, this is assumption. We always assume that f lambda is a continuous family of smooth hyperbolic iterated function systems on a compact interval x, and we also assume that the transversality condition holds. So with Barály Balázs and Boris Solomiak and Adam Spivak, we considered the case when instead of projecting one measure from the symbolic space with a family of iterated function system, we consider a family of measures which depend on the same parameter as the which appears in the iterated function system. So one more time, what we did here, it was basically we considered we consider the family which depended on this parameter, and previously what we knew it was, I think I would cancel this, and so what we considered previously it was that we had a measure. So we had a measure mu on sigma, and we had this family of iterated function systems where lambda was from u, and there was this corresponding projection from sigma to lambda lambda to the attractor. And what we considered with Solomiak and Urbanski, it was that we considered the push forward measure of this mu. So in this way, we called it nu lambda, and we wanted to and we investigated the dimension of this nu lambda and the absolute continuity of this nu lambda for various parameters. But here we just push forward one particular measure. Now, if you have a family, then for different members of the family, for different lambdas, for different iterated function systems, it can happen that the measure which is relevant for this iterated function system is different. Previously, we spoke about the situation when mu was the Gibbs measure for the geometric potential. So the geometric potential, which was the geometric potential, was this. This was the geometric potential, and the geometric potential depends on the parameter. So the Gibbs measure for the geometric potential, if we come back to here, the Gibbs measure for the geometric potential depends also on the parameter lambda. So our earlier result with Solomiak and Urbanski could not handle this situation, because then there was one fixed measure which was projected by this push forward, but for the same measure was pushed forward for different with different pi lambdas, and then what we did now with Balázs Bárány, Boris Solomiak, and Adam Spivak, that we considered for every parameter different measures, and that was pushed forward. So it's this is our theorem that if mu lambda is a family of Gibbs measure on sigma, and there are some regularity properties I would not like to read out now because I do not have that much time. So, but if you take this family of Gibbs measures and then you push it forward, so these Gibbs measures, the measure itself does depend. So it is like you have a different measure. You have different measure for different lambdas. This is the novelty, what we did here. And then you push forward different measures for different lambdas. And then still the Hausdorff dimension of the push forward measure is what it needs to be for almost all parameters. And if the similarity dimension, because here I say that the dimension of the minimum of the similarity dimension of the measure and 1, but if the similarity dimension entropy divided by Lyapunov exponent is bigger than 1, then this push forward measure is absolute continuous for almost all parameters. This was one result that we proved. Yes. So as a corollary, if we take the measure, which is because the previous more general theorem was about Gibbs measures for certain potentials which are smooth enough uniformly, but as a corollary, what we get is that mu lambda is the equilibrium measure for f lambda, which means that mu lambda is the Gibbs measure for the geometric potential. So if the mu lambda is the Gibbs measure for the geometric potential, which is the most important measure, then for Lebesgue almost all parameter, the push forward of the equilibrium measure is indeed the minimum of 1 and the similarity dimension. And if this SF is bigger than 1, then the push forward of the equilibrium measure is absolute continuous. Okay. So I just like to mention that all of these things what I have spoken all until now are about hyperbolic iterated function systems on the line. But interestingly, these results give something new even for the self-similar case. So this is the self-similar case because when we consider the self-similar iterated function systems, a subset of this hyperbolic iterated function system. Simply the difference is that when we talk about, oh my God, just a moment. like, yeah. So the self-similar systems are like this is so this is an interval X, and a self-similar system is something like this. This is a straight line, and this is a straight line, and this is a straight line, like that. This is a self-similar iterated function system, and then these hyperbolic systems we considered are the ones when the graph of these functions are not straight lines, but something like more general, something like this, this or that. So this is the hyperbolic, and this is the self-similar system. But whatever we proved, it is for the hyperbolic setup, but it gives something new also for the self-similar situation. So this is the self-similar. Then now we assume that the contraction ratios are between 0 and 1, and then the similarity dimension SF is just the solution of this red equation, and then we can consider a probability vector, and this is the most natural probability vector when you see that when S is the similarity dimension, then this equation holds, and these elements which you add up can be chosen as probabilities. So this the corresponding probability vector is P, and then previously Neinhauser and Nagai Wang considered transversality regions and absolute continuity of the push-forward measure of this measure, but they always push forward the same measure. And also there was a paper by Saglietti, Shmerkin, Solomiak, where also they considered non-homogeneous self-similar iterated function system and the push-forward measure of a Bernoulli, infinite Bernoulli product measure, but also they push forward the same measure. So the conclusion of our theorem with Balázs Bárány, Boris Solomiak, and Adam Spivak, that if we consider such an iterated function system, which is a one-parameter system, so you see that this is the contraction ratio depends on the parameter, and may or may not depend, but one of the two is not constant in lambda. So this is the translation part, and we assume that this is not degenerate, so the fixed points are not the same, and satisfying smoothness assumptions. Everything is, let's say, 3 times continuously differentiable and transversality condition, then the natural self-similar measure. So one more time, what is the natural self-similar measure for a certain parameter? So for a certain parameter, lambda, I'm sorry, so for a certain parameter, here is the contraction ratio Ri lambda. This is the contraction ratio, and you raise it to a certain power S lambda, and you add up j from 1 to m, and this is equal to 1, and you solve this equation, and the solution of this equation is it gives you S lambda, and then you write the P, which is a probability vector. It depends on lambda, and the components of P, the i's component of P, Pi, which is the i's component, is Ri lambda raised to the power s lambda. This is the ice component of p lambda. So this is the natural measure. If you take the mu, which is p lambda raised to the power n, this is the natural measure mu lambda. Better to say mu lambda, because this measure depends on lambda. This is the natural measure for the parameter lambda, and you push it through, push it forward, so you form nu lambda, which is pi lambda star mu lambda. So you consider this self-similar measure, which is the natural measure, and then what our result gives it is that this is absolute continuous with L2 density for almost all parameters lambda, where the similarity dimension is greater than 1. Okay, so this was one application of our result, and then we can consider somehow a very special case of the previous claim, namely if there are only two mappings, so M is equal to 2 in this case. So what I write, M is equal to 2, and there are only two mappings, lambda 1x and lambda 2x. And then we would like to consider the natural measure. So what is the natural measure? You solve lambda 1 s plus lambda 2 s is equal to 1, but of course this s depends on lambda 1, lambda 2, so s is a function of lambda 1, lambda 2, because S is just the solution of this equation. And then you say that this is P1 and this is P2, and then you consider the probability vector P1, P2, because they depend on lambda, so they depend on lambda. So you consider the probability vector, let's say P lambda, which is P1 lambda and P2 lambda. This is the probability vector, and then let's say mu is P lambda to the power n. This is mu, and then but this is also dependent on lambda, and then you can define nu, which is the push forward of mu lambda. So this is the natural measure. This is the natural measure, and we can ask about the absolute continuity of the natural measure. And what follows from our result, and this is interesting that even for self-similar, it gives something new. So what follows from our result, it is that if you consider this is in lambda 1, lambda 2 plane, so here it is lambda 1, and here it is lambda 2, this is 1, and this is 1, and you consider this line, and also here, oh my god, and also here we draw 0. This is somehow the bound for transversality. So 0.668, and here also 0.668, and you draw this line, as you can see here, and you consider this orange region, and for almost all Lebesgue, two-dimensional Lebesgue measure, almost all pairs, lambda 1, lambda 2, which is chosen from this orange region for almost all value, this natural measure, push forward natural measure, is absolutely continuous with L2 density. There was one more chapter I wanted to talk about, but my time is over, so is up. So thank you very much for your attention. I finish it here.
Yes, thank you very much for giving a nice talk. So, any question from the participants? Thomas, do you have any question? Radhu?
No, thank you. Very nice talk.
Yes, good.
Thank you very much.
Yes. So let us thank the speaker again for giving a nice presentation. And
Thank you.
so we'll meet again next week. Bye,
Thank you.
everybody. Yes, thank you.
Thank you. Goodbye.
Bye. Bye.
Goodbye.